Hydrolysis of proteins. Here we see the destruction of the primary structure, whereas denaturization got rid of the quaternary, tertiary, and secondary structures. Only hydrolysis actually chops up the primary structures, and we're actually breaking apart the peptide-amide bonds and producing free amino acids. Basic and acidic hydrolysis are both possible, and this occurs during protein digestion. So tests for proteins and amino acids. The xanthoproteic test, we use nitric acid. And there are yellow products for proteins that have benzene rings, like phenylalanine or tyrosine. The Burette test with copper-2 sulfate. There's a violet color for peptides and proteins with 2 or more peptide bonds. The test is negative for amino acids and dipeptides, because a dipeptide only has 1 peptide bond. Lowry assay, copper sulfate and molybdates and tungstates. A dark violet blue color for tyrosine appears, or tryptophan containing proteins will also give you a dark violet blue color. The Bradford assay, Kumasi brilliant blue dye in the Bradford assay. This is a dark blue color for proteins. This is the most sensitive common test for proteins, so it's used quite a bit because it's pretty cheap. Ninhydrin test. This is also a great test for proteins. You get a blue solution for all amino acids except proline and hydroxyproline, because if we remember, proline was unique in that it didn't have a free amino group like all the other amino acids. Separation of amino acids by chromatography. Here we have thin layer chromatography, paper chromatography, and column chromatography. And as the solvent moves up, it brings amino acids up with it. Separation of amino acids by electrophoresis. We can separate proteins on the basis of a difference of size or charge. So, the positive proteins will move to the negative electrode. The negative proteins will move to the positive electrode, and so we can separate them by charge. Electrophoresis is very sensitive and a precise method. And basically in electrophoresis, you put your proteins into a polyacrylamide gel and you run electricity through it, and the amino acids and small proteins move through the polyacrylamide gel. The bigger they are, the slower they move, and this can separate them into bands. Determination of primary structure of proteins. Here we have Sanders reagent, 2,4-dinitrophlorobenzene. This will react with the amino group of the N-terminal amino acid of a polypeptide chain. After hydrolysis, the terminal amino acid remains with the dinitrobenzene group and can be identified. So you have your protein, and then we add our dinitrofluorobenzene, and it links up. Then we hydrolyze it, and we get our terminal amino acid is known. Then we can chemically chop off the N-terminus and repeat this again to figure out what the next amino acid is. Then you can chop that off and run this reaction again and figure out what that last amino acid is. And so if you have 60 amino acids in your polypeptide, you have to do this 60 times. Every single time, you're only identifying what your absolute N-terminal amino acid is. Edmond degradation, the separation of amino acids one at a time from the N-terminal end of the polypeptide chain. And phenyl isothiocyanate is added to the N-terminal amino group, as we see here. And then it chemically reacts, and the N-terminal amino acid addition product is cleaved from the polypeptide chain, which is isolated and identified. And so you can do this over and over and over again. So you're basically removing just the N-terminal amino acid one at a time. And so you have to do this as many times as there are amino acids in your protein. But each time you'll know what the identity of that amino acid is, and so you will know the primary structure of your protein if you do this. It's long, laborious work, but it does yield good, accurate results. So 3 rounds of Edmond degradation yield serine, glycine, and histidine. And then if we do hydrolysis, we see that we have histidine, glycine, threonine, phenylalanine, histidine, proline, and serine, glycine. And so now we have to put them together. So we saw the serine and the glycine, which is here, and that is our N-terminus. And in the Edman degradation, we saw that the third went serine, glycine, then histidine. So we know our first three. And so we know it can't be this histidine because it has a phenylalanine. It's got to go serine, glycine, then histidine. So it has to be this histidine. And so when we put these in order, you'll have serine, glycine, then histidine, glycine, and then phenylalanine, histidine, proline. And so by using two pieces of information, now we know the identity of these 8 amino acids and what order they'd be in. And so this is combining two different techniques to make it a little bit less work. You could just do Edman degradation for all 8, and then you would have the 8 in the order. But by running this and then chopping up into fragments, a lot of times you can figure out the order, because if you get lots of fragments of different orders, you can piece it together and see what the correct amino acid lineage should be. And that is the end of chapter 29.